Hi, everyone, and welcome to this episode of Crowded Beaker Solves. Today, we are calculating wavelengths and frequencies of and energies of light. In your chemistry travels, you'll likely come across looking at some atomic spectra, or you'll likely do some flame testing where you stick elements in the flame and see what colors they make. The purpose of all that is to see the colors and identify elements based on their colors. Atoms have their own signature colors they like to give off, and those colors are in the form of photons of light. And so sometimes we have to calculate the wavelength of it, or the frequency of it, or even the energy of it. What's the energy of a photon? Maybe an atom is emitting, and that can give us an idea of where the energy levels inside the atom fit. So you might see a question something like this. A photon of green light has a wavelength of 504.2 nanometers. And what is its frequency and energy? So, a quick little background. You'll probably be provided with a formula sheet. Here's one from the AP chemistry class that I teach. And it has some information up here like nanometers and milliliters and some pressure units. These are the equations we're going to be using for this. The first one is E equals HV, or nu, that's actually the Greek letter nu, which we use for the frequency. E is energy, this letter is frequency, and then this thing that looks like an upside down Y, it's the Greek letter L, is for we use for wavelength. There's also a couple of constants that we're going to need for these calculations as well. You don't have to memorize those constants, I don't think. I don't make my students memorize those constants, but we have them available as tools should we ever need them. So we're going to start, since we know the wavelength, we're going to start by calculating the frequency using this second equation. And then we're going to use the frequency and plug it into the next equation and solve for the energy. So that's what we're doing. A couple of little tools that we have. The first thing, though, I'm going to need to do, the wavelength, because the constant here is in meters per second, I need to have my wavelength in meters. So I'm going to go ahead and take a little detour for a second and just do a quick unit conversion. This is something you'll probably have to do as well. Because we often give photons of visible light their wavelengths in nanometers. So we just get nicer numbers to work with. Okay, so how do you go from nanometers to meters? Well, it turns out there's a billion, or 1 times 10 to the ninth nanometers in 1 meter. So you just have to, in this case, divide by a billion to get it in meters. The numbers don't change, the decimal place does. 5.042 times 10 to the minus 7th meters is what it's going to end up coming out as. You'll have a chance to practice that in the sample question coming up next. Okay, now that we have that in meters, I'm going to set it up using the equation that is in my toolbox. C equals wavelength times frequency. And what this says is the wavelength and frequency are indirectly related to each other. This is a constant, so if the wavelength goes up, the frequency would have to come down and vice versa. So the constant is just given to us. I'm just going to round it up, 3.0 times 10 to the 8th meters per second. That's the speed of light. We use the letter C for the speed of light because it comes from the Latin word celeritas, which means swiftness. Light is very fast. And so we're going to plug in our wavelength, 042 times 10 to the minus 7th. And we'll leave the frequency as the variable because we don't know it yet. And if we do our math correctly, give me 1 second to do that. 3 times 10 to the 8th divided by 5.042 times 10 to the minus 7th. You should get a number that's very large. I got 5.95 times 10 to the 14th. And that's in hertz, or seconds to the minus 1. You could also write it as 1 over seconds, or even, like I said, hertz is also a possibility. And those are all equivalent units. But for visible light, you should get something times 10 to the 14th as your exponent. And that's 595 trillion times that little photon is going up and down every second as it travels. Now, once we know the frequency, we can then find the energy, because the frequency times a constant gives me the energy. And that's Planck's constant, named after good old Max Planck. and we can set up our equation. Always do your grader or your teacher or your professor a favor and write down the formula that you're using, and then show the substitutions of the things you know, and then solve. It just makes it nicer so that people don't have to think too hard about what you're doing. All right, so the energy is Planck's constant, 6.6262 times 10 to the minus 34th, which is a really weird number. Very small. And then we can actually just plug in our frequency we just found, 5.95 times 10 to the 14th. So this is joules times seconds, and this is 1 over seconds. So the seconds is going to cancel, and we're going to be left with joules. And I end up with an energy of 3.94. And again, I rounded all of my coefficients to sig digs. My calculator gave me like 1,000. So times 10 to the minus 19th joules. And of course, you want to set off your answer with a little heart, just to let people know that you're done and that you love your answer. Okay, so that is an example of calculating the frequency and energy of a photon given its wavelength. So now it is your turn to do exactly the same thing with just a different starting value. The first photon was a photon of green light. This will be a photon of red light, 637 nanometers. So take a moment, pause the video, see if you can work your way through these calculations again, and we'll check the answers in just a second. Okay, so I'll unveil the answers, and if you were able to do it, you should have converted it into meters, 10 to the minus 7th meters. So you divide by a billion. You get 4.71 times 10 to the 14th hertz, or cycles per second, as your frequency. Plug that in down here with the same constant, and you get another number times 10 to the minus 19th. 3.12 is the coefficient there. So if you're able to do that, congratulations, good job. And we'll take a look at another example, something like this, in our next video. In the meantime, happy solving, and have a great day.